The new topic is power series. And a power series is like the series we were looking at with an addition to it. So before I get to power series, I just want to remind you of some series that we looked at. So a little review of the infinite series we've been playing with. If I have the sum as n goes from 0 to infinity of 1/2 to the power n, that's going to give me 1/2 to the 0, which is 1, plus 1/2, plus 1/4, plus 1/8, and so on. What kind of series is this? This is a geometric series, right? And we have a formula for geometric series convergence under certain conditions. If the ratio that we're raising the power to in absolute value is less than 1, then we have a convergent series. It's the geometric series test. And even better, the geometric series test that says that the convergent value is always the starting number, which we call A, divided by 1 minus R. R is that ratio. Well, my starting number is 1 minus my ratio of 1/2 that I'm multiplying by repeatedly. 1 minus 1/2 is 1/2. 1 divided by 1/2 is 2. This series should converge to 2. So if I look at any partial sums, they should be getting closer and closer to 2. Let's look at another example. The sum as n goes from 1 to infinity of negative 3/7. The end. What would that look like? Let's start with 0, actually. Negative 3/7 to the 0 is 1. Then we'll get minus 3/7. Then we square it and we get a plus 9/49. And then we'll cube and we'll get some other value, dot, dot, dot. We keep going. This is geometric. My R here is in absolute value less than 1. So the convergent sum of this, it is convergent, and its sum is the first term 1 divided by 1 minus a negative 3/7, which would be plus 3/7. 1 plus 3/7 would be 10/7, and if we flip 10/7, we get 7/10. So we should see when we look at partial sums of this, it should be approaching 0.7, closer and closer and closer. Now, bottom line is, for any R that is less than 1 in absolute value, I have a convergent series, right? So in general, if I just keep this geometric series simple, n equals 0 to infinity of R to the n, that will be 1 plus R squared plus R cubed, and so on, like the two examples above. And since I picked the starting term the way I designed it of 1, it's going to be 1 over 1 minus R. Now we use R for ratio because we're looking for a ratio between 0 and 1 or negative 1 and 1. But I don't have to use R. I could write this instead as the sum as n equals 0 to infinity of x to the power n. So all I'm doing is replacing an R with an x. So that would be 1 plus x squared. Oops, I made a mistake there. I'm missing a term. This would be the 0 term. I'm missing my first term. That's the second term. That's the third term. Typo. Okay, let's squeeze in here. A 1 plus R is what this should look like, then plus R squared. So this one here should be 1 plus X, and then plus X squared. Got to get those powers in order, plus X cubed, and so on. And this will converge to 1 over 1 minus X if, according to the geometric series test, the absolute value of X is less than 1. Now, if I do a partial sum on this series right here, for example, what is S3 for this sum? Well, it would be 1 plus X squared plus X cubed. This is a polynomial. Polynomial. My claim is that this polynomial right here looks a lot like that function right there. Not exactly, but close. I only get the equal if I add infinitely many of them. I only stopped at 3. Let's graph these two and see what they look like. graph for today is Desmos, and I want to graph 1 plus x squared plus x cubed. Looks like that right there. Let's compare that to the graph of 1 divided by 1 minus x. And what we can see here is if we zoom in between -1 and 1, they're pretty tight. How would I get them tighter? I would just add more terms. Throw a plus x raised to the 4th on here. And they get tighter longer. Let's adjust my screen a little bit. Let's go with y up to, say, 1.5. Oh no, I want to go higher. Sorry, I want to go up to like 10. That's better. If I want them tighter, I just add another term in the series, x to the 5th power plus x raised to the 6th power plus x raised to the 7th power. So the more terms I add, the farther I take this partial sum out, the closer this polynomial gets to matching the shape of this rational function. The idea of a power series is to take the idea of series, infinite series that we were working with, those were just series of numbers, and instead look at series of variables. So basically a power series is an infinitely long polynomial. And this is one example of one that happens to match a function we already know. And it turns out there are many power series that don't match functions we know, which means they create a whole new series. So power series is an infinitely long polynomial. The general version of a power series looks like this. There's some constant term out front. Then we have another constant times our linear term. And I'm going to put in x minus a there. Then we're going to have our next constant times our quadratic term, x minus a squared, plus our next constant, we'll call that C3, times our cubic term. And we keep doing this forever. So it's a series, but a little more general than just a series, because now I have this other variable x in there. So I could use summation notation on this. This would be the sum as n goes from 0 to infinity of Cn, one of the constants, times x minus a to the nth power. And this is called a power series centered at a. Often we'll look at power series centered at 0. If we center it at 0, we'll just get an x to the power n. But it could be centered somewhere else. Now, as far as convergence of a power series goes, there's 3 cases. Case 1 is that it only converges at a. And diverges elsewhere. So that's like the worst case scenario. We really don't have a series. Didn't work. 2, it could converge for all real numbers. We'll look at some cases like that in a minute. Now, my previous series here that I looked at didn't converge for all real numbers. It only converged for x values in absolute value that are less than 1. In other words, the x value had to be between 1 and -1. So it didn't converge there, didn't converge there, it converged everywhere in between but didn't work out here and out here, right? That was our construction of a geometric series. We proved that a while back. So in other words, x has to be between -1 and 1. So the third case with power series, which probably happens more often, is that we get an interval of convergence. Now, since that interval has a center, kind of like this example back here, this one right here would be centered at 0. So 0 would be the center, and then we can reach out to the right by 1 and reach out to the left by 1. That 1 is called my radius of convergence. So generally with power series, we're going to have a center of the where it converges, and we're going to have a radius out from that. The two of those build part of the interval, and then we have to consider the endpoints. So a little more note on this. As far as an interval of convergence, that's going to look something like this. The absolute value of x minus a is less than r. So that's the basic interval. A here is the center of the interval, and r is the radius of the interval. So if we look at a number line, right in the middle is that value a that we're centering at. Often we'll center at 0. So this inequality then says from a, we're looking for any x value whose distance from a is less than r. That means I can go as far out to the right as a plus r, or as far out to the left as a minus r. So all the numbers in here are good. If I pick any of those values, I'll have a convergent series. We'll check that in a minute on a couple of cases. The endpoints have to be checked separately. Sometimes they diverge at the endpoint, sometimes it converges at the endpoint, sometimes it's one or the other. So we have an interval of convergence, which has a radius, and endpoints are variable. So endpoint convergence varies. Check the endpoints. So generally what's going to happen with this power series is we're going to try to find the radius convergence. Once we have the radius of convergence, we find the interval. We certainly have the inside of the interval. We have to check the endpoints to get the entire interval. So again, for any particular series, we always have to double check what's going on at the endpoint. Sometimes they converge, sometimes they don't. And these two cases are what we're going to mess with most of the time. The hardest one is that finding the whole interval of convergence. Interval of convergence here. Notice that I went up to the 7th term here, and the sequence is pretty tight. More so it looks toward -1, less so as we get to 1. And if I wanted to get tighter in terms of matching its function, I keep adding terms on here.